harmonics, in fact, this section is about standing waves. Yani 3/4 is the basic of this section. Only these standing waves will form in instruments, string instruments and pipes. The first instrument which we are going to study is string instruments, yani string fixed at both ends. So before studying this, let's remember something. Standing waves on a vibrating string generates the sound. On a vibrating string generates a sound. And as you plug a string, not only one, more than one standing wave form on the string. Yani several possible vibrations may form on idealized string. Idealized string is, it's a string of an instrument. Yani every string doesn't do that. It must be vibrating strings. And as I said, standing waves produce the sound. So let's remember the standing wave patterns from chapter 3, section 4. The first order standing wave, only one loop. Next one, 2 loops. Next one, 3 loops. Next one, 4 loops. It goes on like this. Yani from first order to second order, we are going to increase the number of loops, 1. If you from one harmonic to the next harmonic, you are going to increase the number of loops, 1. 1 plus 1, 2. 2 plus 1, 3. 3 plus 1, 4. It goes on like this. And because string is fixed at both ends are note. What is note? If there is no vibration. If not no vibration, that point is called note. Because it is fixed, so is it possible for a fixed point to vibrate? It's fixed, impossible. So that's why this point is not vibrating. And also, that point is not vibrating. These are notes. But between two notes, there is a point. This point is vibrating with the largest amplitude. And from equilibrium position, this is the equilibrium position, you know. Largest amplitude above in positive y direction, also vibrating in negative y direction with the largest amplitude. This is called anti-note. Yeah. So the ends of the string which cannot vibrate must be notes, and between two notes, the string experiences the most displacement, the greatest amplitude. So this point called as antinote. Between two notes, there is an antinote. This is, in this chapter 3, section 4 is named as first order standing wave. Right now, in musical instruments, we are going to name this not standing wave, harmonic. First, harmonic. From one standing wave to the next one, we are going to add one more loop. Yani 2 loops. So this is second order standing wave, now named as second harmonic. Again, the points which do not vibrate, note, and note, and note. Between two notes, again there, the point, one point is vibrating with the largest amplitude, antinote. Between two notes, antinote. Or between two antinotes, again note. Again, between two antinotes there is a note. Between two notes there is an antinote. This is second order standing wave, or named as second harmonic in this section. Then going to the next one, third harmonic, third order standing wave. How many loops are there? 1, 2, 3. Did we add one more loop? Yes, we did. And in string instrument, fixed at both ends, because all the string instruments are like this. Ends are fixed. So as you see, note is 1 greater than antinote. Note is in here is 3, but antinote is 2. In here, note is 4, but antinote is 3. Then we say that number of notes are 1 greater than number of antinotes. Then, this is what we know from chapter 3, section 4. From one note to the next note is half wavelength. Half wavelength. If you look at the pattern, it is similar to just one pulse. A wave is produced by 2 pulses, remember? 1 pulse up, 1 pulse down. This is 1 lambda. Yani 2 loops together makes 1 lambda. So 1 loop, lambda over 2. Another loop, lambda over 2. Then it makes that. From note to note, lambda over 2. Note to note, lambda over half lambda. From antinote to antinote, also lambda over 2. It's like this. Half of the pulse is on the left, half of the pulse is on the right. Yeah, it makes one pulse again. From nth note to nth note, it is again lambda 2, lambda over 2. What about nth note to note? Nth note to lambda over 4. It was the mystery question, still valid in here. And distance from one note to next, or distance from one nth note to next, is always half a wavelength and lambda over 2, which is equal to length of a single loop. One loop always equal to, it doesn't matter which instrument you are talking about. String instrument, pipe, open at one end or close at one end. So they are always equal to lambda over 2. And let's study the patterns in details. But first, when we do this experiment in the classroom with the spring, this pattern was the first pattern we catch. This pattern happens at the smallest frequency. Maybe you remember my hand was vibrating at the slowest rate, smallest frequency. This is first harmonic, and the frequency which produces the first harmonic is named as fundamental frequency, the lowest frequency that produces standing wave. Of course, which one? First harmonic. It's called as fundamental frequency, and we represent it by F1. Remember, standing waves form not at every frequency, at some certain frequency, at also some certain wavelength. And wavelength of this wave, which produces the first harmonic and single loop, this standing wave will form at longest wavelength, called as fundamental wavelength. Yes?
Lowest frequency isn't lowest tune?
Sometimes you say that it vibrates lowest tone.
Yeah,
Lowest tone, yes, right. Lowest tone, first harmonic. Lowest frequency happens at the lowest tone. But because frequency is the smallest, wavelength must be longest. According to which equation? V is equal to lambda times F. If this is smallest, wavelength is longest because speed of the wave in the medium is unchanged. If you don't change the medium, if you don't change the property of the medium, speed is unchanged, which is going to be the string in here. Okay, then let's remember the patterns. First harmonic, 1 loop. Second harmonic, 1 plus 1, 2 loops. Third harmonic, 2 loops. Always we are adding 1 loop. Now let's get the wavelength and frequency from first harmonic. Okay, as we said, length of a single loop is lambda over 2. Yeah, from one note to next note, lambda over 2. This length is lambda over 2. But this is the wavelength of the first harmonic. First order standing wave, first harmonic. I will write in here lambda 1 over 2. It's equal to length of the string. From here to there, it is the length of the string. Then we will make them equal. We'll make them equal. How? Lambda 1 over 2 is equal to length, cross product. Lambda 1 is equal to twice of the length of the string. Also, you can get this lambda by using the equation which we studied in chapter 2, section 4. What was the equation? Lambda n is equal to 12 over, do you remember? So n is equal to 1 in here. First harmonic. When we write in here 1 and 1, what happens result? 12. Yani, what is the longest possible wavelength which produces a standing wave on a string fixed at both ends? It is 12, which is the wavelength of the first harmonic, as she said, lowest tone. Then, what about frequency? Okay, we defined this pattern wavelength. Also, we should define in this section frequency. So I'm going to use the equation which relates frequency and wavelength of a wave, which is equal to lambda times frequency is equal to speed of the wave in the string. So then it's first harmonic, and lambda 1 times f1 is equal to v. Then write this equation for frequency is divided by lambda 1. How much is lambda 1? Then we got the equation. We got the equation of the first harmonic's frequency divided by 12, which is also known as fundamental frequency. Yeah, the fundamental frequency is going to be v divided by 12. Then next harmonic. Okay, I can continue. How many loops are there? 2 loops. Each loop is 1 over 2. Half lambda plus half lambda, 1 lambda. Yani from here to there, this is 1 lambda. Also, it makes like a one wave. Look at this. 1 pulse up, 1 pulse down. What is this length? 1 wavelength from here to there. Or for red, you can do for red as well. 1 pulse up, 1 pulse down. It's 1 lambda. Yani in the second harmonic of the string fixed at both ends, length of the string is equal to lambda 2. Next one. Okay, you can make them equal, you can find it. Okay, then let's try the equation. Lambda 2 is equal to L. Lambda 1 was 2L. Lambda 2 is equal to L. What happened? We divided this by 2. Yani, second harmonic's wavelength is going to be half of the first harmonic's wavelength. Lambda 1 over 2. But if the wavelength is changing this way, frequency must be changing opposite way. If wavelength is half from first to second, and divided by 2, frequency must be doubled. Yes. Second harmonic frequency is going to be twice the fundamental frequency or first harmonic frequency. And this series goes on like this. From one harmonic to the next, we always increase the number of loop 1. 1 loop, first harmonic. 2 loops, next one. And its wavelength is lambda 1 over 2, frequency is twice. Third harmonic, lambda 1 over 3, frequency is 3 times. Fourth harmonic, lambda 1 over 4, frequency is 4 times fundamental frequency. It goes on like this. Yani, if you want to find frequency of the all harmonic series can be formed at this string whose length is L, in which through which the wave is moving with the speed of V, we are going to find n times V divided by 12. What is V divided by 12? Which is the fundamental frequency. And all harmonics are present. What does it mean? First, second, third, fourth, fifth. In a string instruments, all harmonics are present. What is a string instrument? Best example is guitar. Guitar is a string instrument. Violin is a string instrument. When you are playing them with strings. These are string instruments. And according to this equation, frequency of the harmonic series depends on 2 parameters. I am not talking about frequency of the just one frequency. Harmonic series. On first, second, third, fourth, fifth, all of them. All of them depends on 2 factors. One of them is the speed of the wave in the string. Second one is length of the string. So everybody knows about the length. When you press the guitar's different position on the guitar arm, you are changing the length. If you press it closer to the body, you make the length shorter. If you make it far, you make it longer. So as length increases, frequency of the harmonic series should decrease. You are going to get a low pitch sound. But if length decreases, this time frequency of the harmonic series should increase. One of them is this, length. This is how they play the guitar or any other instrument. Or speed, and also speed. What is speed? Speed of the wave in the string. So how can we change speed of the wave in a medium? Properties of the medium. For string instruments, generally this property can be changed by tension. It's not our curriculum, in fact, but when we increase the tension, speed of the mechanical wave changes. Because why? Because of that, when you stretch it, when you stretch it more and more, you are going to hear a high-pitched sound. Because speed increases when tension increases, because it starts to vibrate faster, and that's why sound becomes high pitch. Note that this V in the equation is not speed of the sound in the air. It is the speed of the wave, mechanical wave, which is traveling back and forth in the string instrument. And of course, source frequency and sound frequency must be same. Source is in here, the string. So sound is the music coming from the string. So their frequencies are the same. This was the first thing we learned when we are talking about the wave frequency. Wave frequency, sound frequency depends on only the source, which is the frequency of the harmonic series. And this is string instrument. And better to note this from one frequency, the next one, what is the difference? This is F5. This is twice of F5. This is 3 times of 5. What is the difference between two adjacent harmonics? Yeah, 1 F5. 2 F5 minus F5. 1 F5. From 3 to 2, again, 1 F5. Yani, I don't know, I put it in this quiz or not. I give one question, maybe in test one. So if adjacent two harmonics have frequency, for example, 100 hertz, which is one of them. Next one, 150 hertz. Adjacent harmonics. What is fundamental frequency?
100.
What is the difference between them?
50.
50. Difference between them. 2 F1 minus F1 is F1. This is 150 minus 100. What is the difference? Difference between two adjacent harmonics is going to be the fundamental frequency. We don't care which harmonics are there. We care, are they adjacent or not? So, separation between two adjacent harmonics is equal to fundamental frequency. We have to know this. Next instrument which we are going to study is pipes. The title is Standing Waves in Air Globe. Before starting this, one thing I have to say about the previous titles. These standing waves are transverse standing waves. Because the string is vibrating up and down, wave is traveling along the string. That is the transverse standing waves. But in pipes, it's going to be opposite. In pipes, we have longitudinal standing waves, which makes the sound. How can this sound is produced? It's very easy. Just we're going to make a disturbance. This is a pipe, a short one. You are going to blow it, and you are going to make a disturbance. And this disturbance will start moving back and forth between two open ends. When disturbance is produced at one end of air column, the pipe, it travels through the pipe as longitudinal wave. Yani, when you say that, this disturbance is traveling through the pipe as longitudinal waves. But it's a disturbance. It starts from where you blow, it goes through the pipe, but we know this disturbance is a mechanical wave. Longitudinal has compressions and rarefactions. Compressions, the pressure density higher than normal. Rarefaction is lower than normal. So what's going to happen when these compressions arrive to the open end? Compression is a higher pressure. Normal pressure is outside, so it will reflect back. Rarefaction is lower than the normal, it will reflect back. Yani, when this disturbance produced in the pipe travels through the pipe, and then because of the difference in the pressure, it will reflect back. The longitudinal wave which goes down and reflected waves from the open end, they will interfere and form standing waves like that. Air particles, when I do this, air particles inside this pipe is just doing this, vibrating. But some are not vibrating, you see that? Some particles are not vibrating. So, this particle, they don't vibrate. In here, they don't vibrate. In here, they don't vibrate. If particles have no vibration, these points are called nodes. These are nodes. Nodes. But look at the ends. At the ends, which are open, particles are vibrating with the largest amplitude. That's all. Antinodes. Ends are antinodes. Yani in both end open pipe. This pipe is called both ends open. So ends are antinode because they are vibrating the largest amplitude. That's why we said that. In pipe open at both ends are antinodes. And another antinode we can find. Of course, between two nodes. Yes. And also in here, they vibrate the largest amplitude. Antinodes. Between two nodes, antinodes. So now count them. Antinode, 4 antinodes. 1, 2, 3 nodes. This time it changed. Now antinode is greater than node. Why? Because ends are open, ends are antinode. But in string instrument, it was opposite. Ends were nodes, that's why node was 1 greater, but now ends up antinode. That's why antinode is one greater than node. Okay. So I think we explained everything about it. Now the patterns. We are going to talk about the patterns. And also notice these standing waves in a pipe is longitudinal standing waves. So it's a fluid example is given. Fluid is one of the open end, two-bowed and open pipe. Open ends are antinodes. Another antinode. Between two antinodes, there is a node. So first harmonic. So in bowed and open pipe, first harmonic has two antinodes, one node. It's still one lobe. How one lobe? This is half. Half on the left. Another half on the right. Together it makes one lobe. Yani just like string instrument all. Only difference is in string ends were notes. Now ends are antinode. There are one lobe. Single lobe. If there is a one lobe, length of the one lobe is lambda over 2. Or from antinode to antinode, it's also lambda over 2. So this length of the pipe for the first harmonic is lambda 1 over 2. It's equal to what? Length of the pipe. This is length of the pipe. From here to there, this is length. It's also already written here. And I'm going to make them equal. Yani lambda 1 over 2 is equal to length. Lambda 1 over 2 is equal to length. Cross product. Did we get fundamental wavelength? Is it the same as string at fixed at both ends? Yes, it is. That's why this equation is also valid for pipe open at both ends. Which equation? Lambda n is equal to 12 over m. Right. If lambda is 12, lambda 1, I find the frequency, we divided by lambda, yani we divided by 12 is the fundamental frequency of the pipe open at both ends. The same as well. Yani in string instruments, string fixed at both ends, and to an open pipe will have same equations. Exact same equations. Next harmonic, from one to the next harmonic, how many loops we are going to add? One loop. So 1.5 plus half, 2 loops. 2 loops makes 1 lambda. Again, next harmonic is lambda 2. Length of the pipe is equal to length of the pipe is equal to what? 2 lambda. Let's do it. Lambda 2 is equal to L. So what happened? Divided by 2 again. So half again. Yani second harmonics wavelength is going to lambda 1 over. So third harmonic again, lambda 1 over 3. Fundamental frequency is V over 12. Next harmonic, twice of that. Third harmonic, 3 times of that. Exactly the same. Harmonics is the same. Only difference between the pipe open at 2 ends and string instrument fixed at both ends is number of notes and antinodes. And also in string instrument, standing waves are transverse. In here, standing waves are longitudinal. And according to this equation, again, frequency of the harmonic steady depends on 2 factors. Speed, again, speed of the wave, but this time, speed of the mechanical wave inside the pipe. It is the medium is air. That's why many questions you are going to say that they will say that speed of the mechanical inside the pipe is the same as the sound. Same as the sound, because medium is the same. When I was talking, medium is air. When I was blowing, medium is air. So that's why both speed will be the same. It's possible. Yeah, in some question you will see that. When they say that, instead of saying that speed of the mechanical wave inside the body, they're saying speed of the sound. Because they're equal. So they don't, make the difference. Because they know that you should know it. Okay. And what about L? L is the length of the pipe. It is the first question, so which some of you did mistake. Eh? There you go. For pipes, what is the length of the pipe? First, we should know that. Length of the pipe is from where you blow until the first open hole is the length, not this. Until the first open hole. But if you close them all, what's happening? You get the longest length from here until They are now longest length. So that's why if the length is longest, what happens? Frequency is smallest.
Open by one by one.
Yeah, now it's going to happen. Open one by one in this. So you are making length short, because length is from this open all the next first open all. Now, much shorter. When I take them all from here until here is the length, not all of them. So length of the air column is from where you blow until the first open key or hole is the length. When we close them all, longest length, the pitch is lowest, but when you open it, what happens? Yes. This is how we play a pipe as an instrument. We are changing the length of the air column, we are changing the frequency of the harmonic series, which is called music. Okay. And flute is similar to a pipe, open at board and by the time, similar, your book says similar because it makes sense. None of them is perfect open end because you are blowing. When you are blowing, you are closing here. It's elegant. That's why you don't say perfectly, it's a perfect open at board end pipe, similar to that one. Okay, and next one is, what is going to happen if we close one end of this pipe? If one end of the pipe is closed, yani this is now to an open pipe. Let me make a sound, huh? Now if I hold it, it's going to be one end closed. What happened to the pitch? Decreases. Yani if you close it, absolutely, frequency of the harmonic series is decreasing, even halved. Halved. Yani as soon as you open, the pitch is rising, which tells you that yani closed at one end pipe has a low pitch than the open one. But why so? What's happening to what happens? So, and this is the simulation you like this best from the song. So as you see, one end is open, but the other end is closed, like I close with my hands. If it is closed, of course, particles in there is no space to vibrate. Yeah, particles which are at the closed end is not vibrating, it is a note. But particles which are open end is vibrating, it's an antinote. Yeah, in closed at one end pipe, antinodes and notes share the ends. One end is antinote, the other one is note. Yeah, they are equal in number. Now we are going to count, you will see that. Okay, let's count other notes, find other notes. This is also note. This is also note. Any more notes? No. And between two notes, antinote. This is antinote. Between two notes, antinote, the largest antinote. Now count. 1, 2, 3. 3 antinotes. 1, 2, 3 notes. Yeah, in one open pipe, equal. Numbers are equal. Number of notes and antinotes are equal to each other. Yes, so closed end is a note, open end is antinote, notes and antinotes are equal. One end is antinote, the other one is note. From here to there, it is like a half pulse.
So that's why we see lambda before.
That also it's the antinote to note.
Wow.
Antinote to note is lambda.
Can you call that one harmonic series?
It's the first one.
It's not
First time.
available.
Ama işte bunu öğrendik işte. It doesn't mean that it was with one law. Böyle bir kuralımız yok ki. Yani it can change depending on the instrument. Right now, it vibrates with one antinote and note is half note. And that's why we are going to say from antinote to note it is lambda 1/2 and which is equal to length of the string. Now we go with the equation. So if lambda 1/2, lambda 1, yani frequency, wavelength of the first harmonic divided by 4 is the length. Cross product. Lambda 1 is going to be 4L. 4L. Let's go back.
Did you do the same as the quiz?
Yeah, I think I gave it.
Yeah, the left and the right.
Yes, yes.
But is that wonderful?
No, this is just we have do the next one. You are going to know that it's in that part. What happened? In bore and open part, and string instrument was 2L. But now 4L doubled. Wavelength doubled. You think you can predict the rest of that? If wavelength is doubled, that's why when I close it, frequency decreased. So, and also we can calculate the harmonics, but I will explain last one later. So this is the fundamental wavelength of one and close pi. So fundamental frequency must be in this case V divided by lambda 1. Lambda 1. So V divided by 4, that is going to be frequency, fundamental frequency of 1 and open pi, or 1 and close pi. You can say more. Now next harmonic, but this doesn't change. From one harmonic to next, you are going to add one loop. No, always from one harmonic to next, add one loop. Am I right? So now this is the first harmonic. Its wavelength is 4L, fundamental wavelength, fundamental frequency, V divided by 4L. But from one harmonic to next, we have to add one more loop. Now let's add one more loop. This is first harmonic. We know lambda 1 is equal to 4L. And frequency is V divided by lambda 1, yani 4L. Next harmonic should have 1.5 loop. We add one loop, one more loop. Let's add now. So, from note to note, it is lambda over 2. So let's add this is lambda over, this is lambda over 2. I don't know which harmonic is this, I will find at the end. From end to note, lambda over 4. The length of the pipe this time is equal to lambda over 2 plus lambda over 4. Let's hit that. Lambda over 2 plus lambda over 4 is equal to length. Denominator, so 2 and 1, we are going to make them equal. 2 lambda plus lambda over 4 is equal to length. Yani 3 lambda over 4 is equal to length. 3 lambda over 4 is equal to length. Cross product. Transfer 3 over 4 other side. So let's make it in here. Lambda for this harmonic is equal to 4L over 3. 4L is fundamental wavelength, first harmonic's wavelength. Next harmonic's wavelength is 4L divided by 3, and lambda 1 over 3. Oh, 3, not 2. We jumped from 1 to 3rd. No second. That's why in close at 1 and part, we are going to say that only odd harmonics are present. One more loop add, it's going to be 50. One more loop add, it's going to be 7. Then this is going to be the harmonic series. First harmonic, lambda 1 is equal to 4L. Frequency is going to be V divided by 4L. Next harmonic is not second, it is third. Third harmonic, this is 3. Some students are doing mistake in here. When they think they are jumping like this. Next harmonic is, teacher, it must be 5. Third harmonic is the 3. Yani, you are not going to jump 3 times. From 1 to 50 are jumping. No. Third harmonic is n is equal to 3. Fifth harmonic is n is equal to 5. Seventh harmonic is n is equal to 7. So, lambda 1, lambda 3, lambda 5 exist. What about the frequency? Also, we will do the same way. So, if fundamental frequency, next third harmonic is 3 times of F1, same rule. Fifth harmonic 5 times of F1, same rule. But no F4 does not exist. Lambda 4 does not exist. Lambda 2 does not exist. F2 does not exist. In one and open pipe, only odd harmonics are present. 1, 3, 5, 7. Of course, we are talking about perfect one and closed pipe. That's why trumpets, saxophone, and clarinets are similar again to one and closed pipe, because when you are playing them, you are closing this one end with your lip, but not completely closed. There are still some openings. That's why we said it's close to, similar to, closed at one end pipe. Okay, now, but one more thing again, let me remind you. Let's maybe make a table about this. Let's remember these three instruments. String. Two and open pipe, wide and open pipe. Both open. One and close. One and closed. Pipe. In string instrument, all harmonics are present. Yeah, n is equal to 1, 2, 3, 4, and so on. In both and open pipe, again, all harmonics are present. 1, 2, 3, 4, and so on. But one and closed pipe, only odd harmonics are present. 1, 3, 5, 7, and so on. In string instrument, both and open pipe, wavelength, fundamental wavelength is equal to 12. Both and open pipe also 12. But in one and closed pipe, 4. Fundamental frequency in string instrument F1, we divided by 12. In both and open pipe, again, we divided by 12. But one and closed pipe, we divided by 4. For wavelength, I can use this equation. Lambda is equal to 2L over N. Common equation. I can use for both and open pipe as well. Lambda is equal to 2L over N. In here it changes. 4L over N, and N is 1, 3, 5. Yes. Lambda is equal to 4L over N is equal to 1, 3, 5, and so on. And in string instrument and both and open pipe, separation between adjacent harmonics is 1 node. You are in F1, next one is 2F1, next one is 3F1. It goes on this way, and separation between them is always 1 node. But one fundamental frequency. In one and closed pipe, it's different. So, first harmonic F1, next harmonic, not F2, F3, which is 3 times of F1. Next harmonic, 5 times of F5. So what's the separation between them? Twice of the fundamental frequency. Yeah, difference between adjacent harmonics in one and closed pipe is twice of the fundamental frequency. Now, timbre, sound quality or timbre. When you blow this pipe, at the same time, more than one harmonics can occur, present, which is. Yeah, the sound coming from this instrument is mixture of many harmonics together. You hear that. In fact, timbre is short definition, mixture of harmonics. Mixture of harmonics. Then you can ask a question to yourself. Why N's sound is different than flute? Why flute sound is different than saxophone, even though they play the same note? Because they have different harmonics dominate at a single time. The mixture of the harmonics are different. In flute, it is open at both and pipe. All harmonics are present, but saxophone close to one end. Odd harmonics, most odd harmonics are present. Some even harmonics do not present. That's why each sound is going to be different than this. Even their intensity of the harmonics are different. Yeah, some harmonics are dominant, which is a very big intensity. Some harmonics are less intensity of the sound. Of course, dominant must be heard by your ear. Human ear is not like this. We are not measuring, we cannot see that, oh, this harmonic, that harmonic. We generally see dominant one in your ear. Yani, in a classroom, if a student is cheering, some students are talking, so which one you are going to hear? The cheering one. This is what humor is. We just detect the dominant one always. So, first, a variety of standing waves can occur when string is set into vibration, not only string, when you blow this pipe. Sound waves from an instrument actually consist of multiple frequencies and harmonics. It's a mixture of harmonics that produces characteristic of sound of the instrument. Yani every instrument is a different correct sound than the other one because of this mixture of harmonics, called as timbre. Other name is sound code. This means question. Tuning fork is the simplest device which makes a sound. It vibrates with simple harmonic motion. That's why it has just vibrating at the first harmonic and then intensity, this intensity. Its waveform is sine wave because of the vibration of the tuning forks are simple harmonic. But other instruments are not just one of them. They have more than one harmonics at the same time. For example, clarinet is given in your book, that's why I showed it. Clarinet is similar to one enclosed pipe. Look at that. What harmonics are dominant? First one, third one, seventh one, 2 and 4 accidental because of these open sides, like an open symbol, also exists. Yani, other instruments vibrate at different frequencies, at different intensities. They have multiple harmonics. But each harmonic is a sine wave, like tuning fork. So each harmonic is a sine wave. The available harmonics add together according to principle of superposition and to give a resultant waveform that is complex. Yani, for example, this is first harmonic. Say that his harmonic. Next harmonic, 200. Third harmonic, 300. Fourth harmonic, 400. When you add them all, just like interference of the waves, instead of these 3 waves, you are going to see a waveform, complex waveform. It's this. We get that. Just this is an example I give you. What does complex means? I explained this to you. Every musical instrument is addition of multiple harmonics at different intensities. Look at the intensities. The most dense, the intense one is third. And the third one is going to be big. Next one is 1. It's a little short, but compared to the second, it's great amplitude. Yani, timbre is coming from a mixture of these harmonics at different harmonics, even different intensities. This is one of the questions. Remember. So the waveform is going to be complex, as you see. This is the waveform of what? Resultant waveform of all these harmonics when they mix together, you get this. Complex, but repeating. So repeating waveform is called periodic. Periodic waveform. All instruments. And when I do that, if you have an instrument, which is called oscilloscope, you are going to see that repeating waveforms like this, just like that. Complex and waveform repeats itself. Fundamental frequency determines the pitch. Yani generally, instruments' fundamental frequency is the most intense one. That's like pitch is close to the most intense harmonic. But it doesn't mean that the others harmonic exist, they also exist. As we saw in here, first, second, third, fourth, fifth, seventh exist. Other harmonics are in music called as overtones. That they don't say first harmonic, then second harmonic. No, second harmonic is called first overtone. Third harmonic is called second overtone. Fifth harmonic is called that one. Like, yani, overtones give you one less number. 2 minus 1 is equal to first overtone. 3 minus 1 is equal to second overtone. 4 minus 1, third overtone. We are going to introduce the number of ones to define the harmonics in terms of musical literature, which is overtone. And In chromatic musical scale, there are 12 notes. All notes have different frequencies. These frequency values are not, this table is not in the book, just for explanation I put in here. There are 12 notes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 notes. Is as you see, again, same note. Do and do. But those belongs to other harmonic. This is the first harmonic do. This is second harmonic do. Yani first overtones do. Bakın şu. This is first harmonic do. Then I will blow a little faster. I will jump from first harmonic do to second harmonic do because I don't open my keys. All the keys are closed, which is do. If you use frequency analyzer, you are going to see that the second one is twice of the first one. So the frequency of the 13th note is exactly twice of the first note. Look at the first note's value, 440. The 13th, 880. You can go, it's not the end. It's not the end. When you jump to third harmonic, 3 times. Fourth harmonic, 4 times. Well, if you measure them, you are going to see that. In each of them, it's jumping from 1 to second, second to third, third to fourth. It goes on like this. Altogether, this interval in music is called
13?
13 included, yes. Why they include it's their problem, not my problem. They define this way. So they said that altogether, this 13 note is called an octave. Yani, in music channel, they define the sounds in terms of octave. They don't use this harmonics, blah, blah, blah. So 1 octave high sound, when they say that, you are going to jump from one harmonic to the next one. This is. Now I'm going to first blow at the lowest tone. Then I will increase the sound 1 octave. I will jump to second harmonic. Now I jump 1 octave. From first to second, it is 1 octave. That's all.